Hello everyone. In this video, I will demonstrate how to perform data screening for multivariate statistical analysis using grouped data such as MANOVA. So we're going to be dealing with screening and examining the data for quality of the data or accuracy and missing values and outliers, and see whether we meet the assumptions of normality, linearity, and homoscedasticity. Why these things are important, I have discussed that in part 1 of my video. So those who are interested, please refer to that video here. In this video, we will discuss about this simple example here. Suppose that we are interested in investigating group differences across individuals who are either very satisfied or not very satisfied with their job. And we want to assess that in our set of dependent variables, which are income, age, education, and hours worked weekly. So education is in years. In part 1 of the video, we discussed the transformation of our income 4. So please refer to that one. And here we are using age2, which is again transformed variable. We are just taking the square root of the age, because while performing the analysis, we saw that the age is fairly symmetric, but it had a high peak. So to take care of that, we just took the square root of the age. So we're not going to do that here. This is just for your information here. I'm referring to this book here. Those who are interested, please go and read the chapter in that book here. So we'll start with our data analysis in SPSS. The first thing I'm going to do is go through each variable. So age is the original variable. We have transformed that variable into age2 by taking the square root. It's a scale level variable. Education is again scale level, and that is in years. And if you see that we are already taking care of the values which are not qualified, so we are dealing here, or addressing as such the accuracy of the data. So we are not considering these values, or these values are treated as missing. Okay. So education is there. Similarly, we did for the age. Hours worked also we did. We took off all the illegal entries in the data or not applicable entries in the data. That's a scale level as well. And the other variable we are dealing with our income 4. This was transformed from our income 91, and those who are interested, they can see the part 1 of the video. And here also we have taken out non-applicable values. They are treating as missing values. So overall, the data quality looks being taken care of here, but we're gonna start working with the missing values. So to conduct the missing values, what we're gonna do is we're gonna go to analyze, descriptive statistics, explore, and we're going to put all our variables there, including dependent and independent. So education is there, hours worked is there, job satisfaction, our income 4, and age 2. Statistics, we want the descriptive statistics. We don't want any plots. I'm going to select here. And this is going to give me a case summary. So in that, we have total 747 cases, out of which only 704 cases have complete values. 43 cases have some sort of missing values in them. So those 43 cases have one of these values missing. Which one we don't know, but even if one variable value is missing, the complete case is denoted as missing. So that's something you have to keep in mind here. We can also do variable wise analysis here. So we're going to go to analyze, report, case summaries here, and we're going to put all our variables there. and we're just gonna say okay here. So this is gonna give me for every variable how many values are missing. So for education, we don't have any missing values, but we see that we have 3 values missing in age 2, and hours work we have 6 values missing. Our income we have 37 values are missing. So in all, this is like, we don't see any pattern. The reason we do this analysis here is to see if we have some sort of pattern going on between the missing values. In general, the data must be missing completely by random. So we don't see any pattern there. In all, 43 cases have some sort of missing values. So this is how you conduct the missing values. We just simply gonna ignore these cases because they're only 5.8% of the cases. So we're gonna perform list-wise analysis, which is the default. So this is how you take care of the missing values. The next thing you have to do is outlier. Now in part 1 of the video, we see how you conduct the outlier analysis at univariate analysis. But while conducting multivariate analysis, we have to deal with multivariate outliers. You can still do the univariate outlier, but we're not going to do that here. It is always good to do that, and from there go to the multivariate outlier analysis. But ultimately, if you are performing multivariate data analysis where you have a group or set of variables working together, it's always good to perform multivariate outlier analysis. So here we have out of 4 metric variable or numeric variable. So what we're gonna do is we're gonna use Mahalanobis distance criteria here to find out the outliers in our data set. Now, how Mahalanobis distance works? Well, what it does, it find the global centroid for all the metric level variables, and from there it sorts of find each case center, how far that center is away from the global centroid, and if it is extreme, then it is considered as an outlier. So what we're going to do here is we're going to go to analyze, regression, linear. We're gonna put our education as an independent, hours worked independent, ID as a dependent variable, or income 4, age 2. Now ID independent variable doesn't make any difference here because we are simply finding the Mahalanobis distance for this 4 metric variable here. We can choose any dependent variable, it does not make any difference here, so we're not going to worry about that. That's why we are choosing the ID here. We'll go to save here, and we're going to say we want to save Mahalanobis distance here. We are not worried about any statistics at this point of time, so I'm not going to do that. I'm not going to select any plots option. We're not worried about any details here. We don't want any details, just we want to save the Mahalanobis distance here. Okay, I guess let's see that here. So these just calculated the Mahalanobis distance here, and see the maximum value was 30.02 and the minimum value was 0.199. And if you go to the data set here, you'll see it has added one more column here. We're going to sort ascending, or rather I would say descending, and see what we have to do is we have to find out how many of this chi-square values are considered as outliers. For that, what we have to do is we have to find the probability value. So what we're going to do is we will find the p-value for each of this chi-square value here, and if that p-value is less than 0.001, then we'll consider that that distance to be an outlier, and we'll exclude that from the analysis. So what we're going to do is we'll go to the data, or transform compute variable. We're going to say lady, I don't know this distance here. We'll say 1 minus here. We will have this distance that we just calculated here, and here the number of variables in the analysis, which are 4. We'll say okay here. So it will go ahead and do that one here. So wherever we have less than 0.001, those will be categorized as an outlier. So these are above all this point, all this value should be categorized as outliers. So we're going to exclude that. The way to do that is I'm going to say data, select cases, if condition. I'm going to say select only those cases where probability is greater than 0.001. Okay. Like I said, it's gonna eliminate these 3 records here that have the missing value, and for other we have a lot of missing values. Those will be ignored anyway because we are doing the list wise analysis, but these 3 are considered outlier because their p-value is less than 0.001, and they should be excluded from the analysis as well. So this is how you perform outlier analysis. Next, what we're going to do is we will move on to the normality assumption. Now again, when you're dealing with the multivariate analysis, you have to conduct sort of both univariate normality analysis and multivariate normality analysis. Univariate normality analysis, we're going to go to analyze descriptive statistics, explore, and we already have all those variables there. We're going to drag job description to factor list because we want to make sure that our dependent variable, each of the dependent variables are normally distributed across all labels of our independent variable, which is job satisfaction, which has 2 labels. So I'm going to say good, we want both here. Statistics, we don't want any outlier here. Plots, this time we will conduct the normality plot, but we will also conduct the Levin's test, which kind of test the homogeneity of variances across, that should be same across all groups for every variable. So we're going to do that as well. For normality test, we will do the histogram here just to check it. So we're going to continue here, say okay here. So it's going to give you a lot of tests here. So here, test of normality. These all values are significant, but this one H2 very satisfied. Looks like this is normally distributed. If the values are significant, that means we are rejecting the null hypothesis and concluding that the distribution is not normal. So only one. Remember that H2 was transformed from age variable by taking the square root. So let's go ahead and check. This looks like it's more normal than other variables. So we can go ahead and check that data here. Let's say histogram here, very satisfied, and that pretty much look normal. So we did pass that normality test here. But other histograms, for example, education here, you can see it's very symmetric, if not normal, a little bit negatively skewed, but it's pretty good here. So likewise, you can do the univariate analysis here, but test of normality here, you see most of them are not normal. One thing you have to keep in mind that the test of normality is very sensitive to the sample size. We have a decent size sample here. That could be one of the reasons we are not getting significant results here. Um, but looking at the histogram, or even the QV plot, we don't see that much deviation from the normality. So at univariate level, we did pass the test, I would say. And likewise, test of homogeneity of variance here. Most of them, in fact, all of them are not significant, which means that we accept the null hypothesis, which means that the variance for all our dependent variable are same across both the groups, very satisfied and not very satisfied. And again, this is done per variable, per dependent variable basis. What we have to do now is we have to perform the multivariate normality test and multivariate homogeneity test as well, and likewise the linearity test. So once you are done with the univariate normality and homogeneity of variance, we're going to move to multivariate normality. And the only way you can do multivariate normality is by visually inspecting the scatter plot. So at most we can do bivariate normality test by visually looking at the scatter plot. The scatter plot should be nice elliptical shape, and if it is an elliptical shape, we can conclude that our data is bivariate normal as well as linear. Okay, so that's a visual inspection. That's very subjective, but still it's better than not conducting any analysis. At least it gives us some idea whether the data is multivariate normal or not. So we gonna go ahead and do that here. So we go to the graph here, legacy here, scatter plot, matrix here. What we're gonna do here is we're gonna put all our variables, metrics, variables here. These are all our interval level scale data. So we have 4 of them, and we want to panel them by, let's say, job satisfaction. Okay, so we don't want anything here. Option, we're gonna exclude the cases list-wise. Okay. Okay, so it's going to produce the bivariate scatter plot. Most of the scatter plots you don't see nice elliptical shape, so normality is obviously questionable. But one thing you can notice here is the data is pretty much symmetric, uniform distribution. So we are, even if we are not looking at a perfect normality or multivariate normality or bivariate normality and linearity, but data is pretty uniform, and we can easily go ahead and perform the rest of the analysis. But this is how you basically gauge the bivariate normality and linearity. And the last thing we're going to consider is the multivariate homogeneity of variances, homoscedasticity. So for that, we have to perform MANOVA. So what we're going to do is we'll go to analyze here, linear model, multivariate, and there what we're going to do here is we're going to put all our dependent variable, education, hours worked per week, income, age, and we're gonna perform that. These are our 4 dependent variable, and our independent variable is job satisfaction here. So we're not interested in building any model. We're not gonna do any contrast, no plots. Options, we're gonna go for homogeneity test. Okay, so this is gonna give us box M test. Okay, so I'm gonna continue that. I'm gonna say okay here. I'm going to go to boxes test of equality of covariance matrices. And this came out to be non-significant. That means we can conclude that the variance in covariance matrices are similar or same across all groups. So here basically what we are doing is we are not comparing individual variables, but we are comparing the complete matrices for all four metric level data or numeric data across the two groups. So it forms a kind of a big matrix for, it's going to form two matrices. So one 4 by 4 for very satisfied, and another matrix 4 by 4 of size 4 by 4 for not very satisfied. And it's going to compare those two matrices. And if the null hypothesis is these two matrices are very similar, and alternatives they are different. So if they are similar, that means the variance matrices are similar or same, or variances are same at a multivariate level across all the groups. One thing you need to notice about the boxes M test is that it is highly sensitive to the departure from normality as well as the sample size. So often it ends up producing significant result if the data is not very normal or if the sample size is too big. So often a very conservative value is used for boxes M test. Use a book says 0.01, but if you do the Google search, often people go as conservative as 0.001. So I'm going to say here, let's say boxes M test is sensitive, and I'm going to go here, boxes M Wikiversity, and here it says that boxes M is highly sensitive. Here it means that departure from normality as such, and also the sample size. So unless p-value is less than 0.001, with your sample size unequal across group, you can ignore it. Ours is much bigger than that, but even if it is significant, yeah, the test is not robust. So this is the conclusion here. Okay, so you have to, if you're getting boxes M result as significant, you have to be not concerned as much. You can still move on because this is very sensitive to departure from normality and as such sample size. Again, a lot of references here that will discuss that. So here, let's, I'm going to say, since right, big M test highly sensitive, so unless 0.01 your sample size is equal, ignore it. Okay, otherwise this test is not robust. Okay, I'm gonna go to other one. Again, other links have better concepts which you can read. Boxes test is sensitive to departure from normality. So if the samples come from non-normal distribution, then boxes test may simply be testing non-normality, which means they're going to give you significant result. I guess this one has more information on that one. So boxes M is sensitive to large data files, meaning that when there are a large number of cases, it can detect very small departure from homogeneity. So it's going to just simply give you a significant result. Moreover, it can be sensitive to departure from the assumptions of normality as well. So that's why we use such a stringent p-value for the boxes M. But here, nevertheless, we don't need to worry because we have a very big value here. This is how you conduct all this data screening process while conducting or performing multivariate statistical analysis, such as MANOVA. So we are using the group data here. So with that, I'm gonna end my discussion here. Thank you very much for listening.